The final type of equilibrium expression we will be looking at, or equilibrium reaction we'll be looking at, is the solubility of solids in solution. As you watched in the Bozeman video, it talked about how when you put solids in water or solids in a solution, they don't all dissolve. They might dissolve a little bit and then some solid will be left on the bottom. We can calculate the amount of solid that will dissolve in a solution by using our equilibrium concepts and ideas and our equilibrium expressions. The equilibrium constant that we'll be looking at is called the Ksp, or the solubility product constant. When we write these, we will look at all of these different solids and the ions that they will dissociate into. So for instance, the first one here, and by the way, this program does not format my subscripts correctly, so all the numbers should be a subscript. But if I take this first solid, which is calcium carbonate, I have CaCO3, and we will look at this solid to see what ions it could break up into when it goes into solution. So calcium is the cation ion in this problem. That will be an aqueous, or aqueous if you prefer, ion in solution, and the other ion in solution will be the carbonate ion. You do not have to write the aqueous subscript, but you definitely do have to write the solid subscript. Then when we write the equilibrium expression for this, we write it as we write every other equilibrium expression: products over reactants raised to their coefficients. So the K expression, specifically the solubility product constant, or the Ksp, is written the exact same way, where the concentration of the calcium ions in solution times the concentration of the carbonate ions in solution are raised to their coefficients. In this case, both the coefficients are 1. There's 1 of each of those ions, and so they'd both be raised to the power of 1, but we don't write those. So this is our new equilibrium expression for solids that are put into solution and dissolving into their ions. The K value is a constant that can be looked up into or in any tables in the back of the book or in the chapter, or you can Google them. All the Ksp values for every solid are known. Again, they're temperature dependent, just like every other K expression has been temperature dependent, and we will do them all very similarly. So if I do one more with you, we have the lead chloride, lead 2 chloride actually, is a solid. That's a solid, breaking up into its 2 ions, which are lead 2 plus, and 2 chloride ions. That's a plus. 2 chloride ions. When I write the Ksp expression now, it's products over reactants raised to their coefficients. So my products are lead 2 plus raised to its coefficient, which would be 1, and the chloride ion raised to its coefficient, which is 2. Now remember, we said products over reactants. Why don't we include the reactants? Because our reactant is a solid, and solids are not included in the Ksp or any K expression. And so the Ksp expression for that one is like so. Try the last one on your own, and then, try the last one on your own, and then I will go over the answer. The last one then, the answer you should get is silver iodide. That is a solid. Breaking into its 2 ions would be a silver ion and an iodide ion. There's 1 of each. It's a 1-to-1 ratio. The Ksp expression for that is products, silver ions raised to their coefficient, which is 1, and the iodide ion raised to its coefficient, which is also 1. That is the new equilibrium expression, equilibrium reaction that we are going to be working with. Our next step is going to be to quantify some of these concentrations in Ksp values.